So, what does probability have to do with safety? Let's think of a few examples. Every risk has an accident probability. What if I were to stick my hand in ingoing gears? What's the probability that I would get injured? There are two ways that you can express probability. You could say that I have a 100% chance of getting hurt, or you could say for every one person who takes this risk, one person gets injured. So this is a 1 in 1 probability. We learn high probability through common sense, through experience. We understand that, and that's why we don't take high probability risks. But let's think of a couple of other examples. What if I took a 6-shot revolver and I put only one bullet in the chamber and I spin the chamber randomly? What's the probability of shooting? It's 1 in 6. There are 6 chambers in the gun and only one has a bullet in it. So this is a 1 in 6 probability. What if I took a deck of cards and asked you to pick a specific card, say the 6 of hearts? What's the probability that you could guess correctly? Well, there are 52 cards in the deck, so your probability of guessing would be 1 in 52. Now, what if on the other hand I ask you to pick an ace? There are 4 aces in the deck, so you would have a 4 in 52 or a 1 in 13 probability of getting it correct. Now, there's another example that I'd like you to think about in a little more depth, and this example is rolling dice. There's 6 sides on each die, so if I roll 2 dice, the lowest number I can roll, adding these 2 numbers on the dice together, is 2. The highest number is 12. But the most likely number, what is the most likely number of all the numbers that you can roll on the dice? And the answer is 7. But why? Because the dice land in combination. There are 6 sides on each die, so there are 36 combinations. But of these combinations, only one adds up to 2. Only 1 and 1 adds up to 2. Only 6 and 6 adds up to 12. But if you go to 7 in the middle of this array, there are 6 combinations on the dice that add up to 7. So while your probability of rolling a 2 or a 12 is only 1 in 36, the probability of rolling a 7 is 6 in 36, or 1 in 6. There's a game they play at casinos that's called craps. And in the game of craps, you roll 2 dice. And the goal is to guess what you're going to roll and to win money, obviously. So the casino says, we'll let you win money if you guess correctly on certain numbers, but there's one number that we want to win on most often, and guess which number they picked? You're right, the number 7. Now, the casino knows that if you roll dice enough times, the number 7 will come up most often. So, what's the formula for winning money from a casino? Roll the dice a lot of times without hitting a 7. That's step 1. Step 2, and this is critically important, take your money and leave the table. Now, if you start winning a lot of money, someone usually shows up and offers you a free drink or some other enticement to stay there. Why would they do that? Because they know the longer you play, the more their chance of winning, because they play the long odds, and they know if you roll enough times, you'll hit a lot of 7s. So, can you learn probability through experience? We're going to use a dice rolling example to show you how that works. What if we didn't know what we've just discussed about the probability of rolling each of these numbers when we roll 2 dice? Could we just roll dice until we learned? The answer is yes, with 2 qualifications. Number 1, we have to roll the dice enough times. If we don't roll enough times, we won't have a sufficient sample to understand what the real probability is. Qualification number 2, we have to keep track of which numbers we roll in which quantities so that we can see what the true probabilities are after our sample is complete. So let's look at this dice rolling demonstration, and let's roll the dice and see what we learn about probability. Okay. The first time I rolled the dice, I rolled a 3. Now, have I really learned anything? No, I knew 3 was one of the possibilities, and that's what I rolled. But is 3 the most likely number to roll, even though I rolled it first? No, we know it's not, but not through our experience. Okay, now I've rolled an 8. My third number is a 6. My fourth number is a 5, then a 9, then another 9. Okay, now this is interesting. The only number that I've rolled twice is a 9. Now, is a 9 the most likely number to roll? I could assume that from my experience, but again, I haven't met the two criteria. Even though I'm keeping track, I haven't rolled the dice enough times to know what the real ratios are yet. So let's roll again. And I've got a 6. Now I have 2 6s, 3 9s, a 10, and another 6. So look at this. This is what my 10 rolls of the dice looks like. Now, what if someone else came along and rolled 10 times? Will their rolls look like mine? Will they match each time that we do this? Let's try it again. And this time we'll speed it up and we'll have the computer roll all 10 times at once. Doesn't look the same, does it? So, two people have rolled the dice 10 times each, and their experiences overlap in some places, but they're not identical. If you got these two people together and said, discuss your experience rolling dice, they'd have some points of agreement and some points of disagreement. So let's bring a third person in and roll the dice 10 times again. Again, our third example doesn't exactly match either of the first two. So if 3 people have rolled the dice 10 times, they may have some points of agreement and some points of disagreement. But the real problem here is that none of these people have rolled the dice enough times. So let's go back and test our theory. If we roll the dice enough times, would it match the probability that we discussed in the earlier example? We're going to roll the dice 6,000 times. Now, theoretically, if the probability of rolling a 7 is 1 in 6, I should roll exactly 1,000 sevens. Let's see if we do. Well, actually I rolled 1,007, but I rolled more 7s than any other number. There'll be a little variation, but the numbers will match the probability curve. I still rolled more 7s than any other number, then 6s and 8s, then 5s and 9s, and the numbers I rolled the least often were 2s and 12s. So what does this have to do with safety? The average worker that we interview can only tell us the detail of 10 accidents at the most. So if each worker is familiar with the different 10 accidents, their perception of the probability of risks will vary. There'll be some overlap and they'll agree on some points, but they'll disagree on most. So how do we overcome that disagreement? We study all the accidents at the site and find out what the real probability is, and we share this bigger set of data with every worker so that we're all on the same page about which is our greatest risk. So how does probability fit back into the cliff analogy? What if I walk out to the edge of the cliff? That's a behavior. What if that behavior has an accident probability, but it's relatively low? I walk out to the edge of the cliff many times and I don't fall off. I don't have an accident. Not having an accident is a consequence of that behavior that will reinforce it. That means that each time I walk out to the edge of the cliff, I will remember that I've done it many times without falling off. So how long will I be willing to take that risk? Probably until I fall off. But that's not always the only answer, because there's another probability involved here also, and we call this the severity probability. Even if I fall off the cliff, only 1 in 30 people who fall off the cliff will be injured severely. So what if I walk up to the edge of the cliff 500 times and then I finally fall off, but I only get a minor injury? There's a chance that based on my perception of the probability, I will continue to walk up to the edge of the cliff until I fall off again and have a more severe injury.